This video offers a mathematical derivation of E equals mc squared. Understanding time dilation. Imagine a standard two-dimensional Cartesian frame of reference positioned on top of a car. Imagine an observer standing at the side of the car, observing it as it drives to the left. The frames of reference begin on top of one another. As the driver sets off, he switches on a torch, which shines a light directly up and out of a sunroof. As the beam of light projects vertically upwards, the car is travelling at a constant and very high velocity. As the light beam in the observer frame of reference has both horizontal and vertical components, the observer sees a diagonal beam. However, the beam of light for the observer appears to be longer. We know that speed equals distance travelled divided by time taken. Rearranging, this means distance travelled equals speed times time taken. We use c to represent the speed of light, t to represent time when a clock held by the observer, t0 to represent the clock which is stationary in the car, and v to represent the velocity of the car. So the distance travelled by the light beam leaving the car is ct0. The distance travelled by the light beam as seen by the observer is ct, and the distance travelled by the car is vt. We can see in the diagram that ct0 is less than ct. As c, the speed of light, is a constant, this implies that t0 is less than t. In other words, time in the moving car runs slower than time for the observer. We now establish a factor which relates t and t0 to each other. We call this gamma and say that t equals t0 times gamma. This can be expressed as gamma equals t divided by t0. Using Pythagoras' theorem, we can see that we have a simple right-angled triangle where the hypotenuse is ct and the other two sides are ct0 and vt. This can then be manipulated as follows. Ct all squared equals ct0 squared plus vt squared. We then factor out t squared and manipulate the equation such that t0 squared divided by t squared equals 1 minus v squared over c squared. Taking the square root of each side, we see that t0 divided by t equals the square root of 1 minus v squared over c squared. Comparing gamma equals t over t0 with t0 over t equals the square root of 1 minus v squared over c squared, we can say t over t0 equals 1 over the square root of 1 minus v squared over c squared. Also, t equals t0 over the square root of 1 minus v squared over c squared. As these algebraic statements relate time within the two frames of reference, these express the concept of time dilation. We know from classical mechanics that F equals ma, or force equals mass times acceleration, and also that P equals mv, or momentum is equal to mass times velocity. So dp by dt, the rate of change of momentum with respect to time, is equal to force. For our purposes, kinetic energy is equal to the work done. To derive kinetic energy, we know that F equals ma. From our equations of motion, we know that velocity squared equals 2 times acceleration times the distance moved, which is v squared equals 2ax, and this can be rearranged as x equals v squared over 2a. So work equals force times distance. Now imagine a force acts on a mass and this produces an acceleration as the mass moves from a point x1 to a point x2 along a straight line. So we can say that the gain in kinetic energy is equal to the work done, which is Fx. Representing F as ma and x as v squared over 2a, we can say that Fx equals ma multiplied by v squared over 2a. Cancelling a from this expression, we arrive at kinetic energy equal to half mass times velocity squared. So, knowing that F equals ma and v squared equals 2ax, we now differentiate this expression for kinetic energy with respect to distance. So, d by dx of a half mv squared equals d by dx a half m times 2ax, as we replace v squared with 2ax. So we can see this equals ma and this equals force. So d by dx of a half mv squared is equal to force. This means that the opposite is true, or the integral from x1 to x2 of f with respect to x must equal kinetic energy. Given that dp by dt equals f and the integral of f from x1 to x2 with respect to x equals kinetic energy, we can now write the integral of dp by dt with respect to x from x1 to x2 is equal to kinetic energy. We know that momentum equals mass times velocity, or P equals mv. Also, in the rest frame of the moving object, dx by dt naught equals velocity. So, in the rest frame of the moving object, we can say that P equals m times dx by dt naught. Using the chain rule, we rewrite P equals m dx by dt naught in the form P equals m dx by dt naught equals m dx by dt times dt by dt naught. In this equation, given that we have dt by dt naught and gamma t naught equals t, we can see that dt by dt naught equals dt naught by dt naught gamma equals gamma. This means that we can now write P equals m dx by dt gamma in the form P equals m v gamma. So we know that gamma equals 1 over the square root of 1 minus v squared over c squared, and P equals mv times gamma. Putting these together, P equals mv times 1 over the square root of 1 minus v squared over c squared. So we can see P equals mv over the square root of 1 minus v squared over c squared. And this is the equation of relativistic momentum. Significantly, we now know that the integral of dp by dt with respect to x from x1 to x2 is kinetic energy, and also P equals mv over the square root of 1 minus v squared over c squared. We now differentiate P equals mv over the square root of 1 minus v squared divided by c squared with respect to time to obtain dp by dt equals d by dt mv square root 1 minus v squared over c squared. We then rewrite this equation in a slightly different form as dp by dt equals m d by dt v multiplied by 1 minus v squared over c squared to the power of minus a half. Using the product rule, we see that dp by dt equals m multiplied by v d by dt 1 minus v squared over c squared to the power of minus a half, plus dv by dt 1 minus v squared over c squared to the power minus a half. Therefore, dp by dt equals mv d by dt 1 minus v squared over c squared to the power of minus a half, plus m dv by dt 1 minus v squared over c squared to the power of minus a half. I've then swapped this round a little bit to highlight the final expression in red, which is d by dt 1 minus v squared over c squared to the power of minus a half. We then investigate the final expression d by dt 1 minus v squared over c squared to the power minus a half, which was highlighted in red. Using the product rule and the substitutions where u equals 1 minus v squared over c squared and y equals u to the power minus a half, we follow the logic through and arrive at the final expression of d by dt 1 minus v squared over c squared to the power minus a half equals a half times 1 minus v squared over c squared to the power minus 3 over 2 times 1 over c squared d by dt v squared. The final part of this expression, d by dt v squared, is pretty inconvenient. We wish to differentiate with respect to time, and all we have to work with is v squared. However, we know that velocity equals acceleration times time, or v equals at. Therefore, velocity squared equals acceleration squared times time squared, and v over t equals a. Also, dv by dt is acceleration. In the second line of the working, we swap v squared for a squared t squared. We then differentiate t squared to obtain 2t. In the final line of the working, we swap a squared for dv by dt times v divided by t. In the second line of the working, we tidy up 2t times v over t to obtain 2v. In the third line of the working, we tidy up 1 over c squared times 2v times dv over dt to obtain v over c squared times dv over dt. Eventually, this simplifies to d by dt 1 minus v squared over c squared to the power of minus a half equals v over c squared dv by dt 1 minus v squared over c squared to the power minus 3 over 2. We then return to our original expression, where the section previously highlighted in red, d by dt 1 minus v squared over c squared to the power minus a half, is replaced by v over c squared dv by dt 1 minus v squared over c squared to the power minus 3 over 2. This leaves us with dp by dt equals m dv by dt 1 minus v squared over c squared to the power minus a half plus mv squared over c squared dv by dt 1 minus v squared over c squared to the power minus 3 over 2. We then rearrange our expression and factor out m dv by dt to obtain dp by dt equals m dv by dt multiplied by 1 over 1 minus v squared over c squared to the power of a half plus v squared over c squared over 1 minus v squared over c squared to the power 3 over 2. We then rearrange this slightly over a single denominator to obtain dp by dt equals m dv by dt multiplied by 1 over 1 minus v squared over c squared to the power 3 over 2. We can see this can now be thought of as dp by dt equals 1 over the square root of 1 minus v squared over c squared all to the power 3 multiplied by m dv by dt. Put more simply, we can see that dp by dt equals gamma cubed times m dv by dt. So we now have this neat expression, dp by dt equals gamma cubed multiplied by m multiplied by dv by dt. In fact, we now have these two tidy expressions. The integral from x1 to x2 of dp by dt with respect to x is kinetic energy, and dp by dt equals m dv by dt multiplied by 1 over 1 minus v squared over c squared to the power 3 over 2. Substituting the second equation into the first, we now have the integral from x1 to x2 m dv by dt multiplied by 1 over 1 minus v squared over c squared to the power 3 over 2 with respect to x equals kinetic energy. This can be rearranged as the integral from x1 to x2 m divided by 1 minus v squared over c squared to the power 3 over 2 dv by dt with respect to x equals kinetic energy. Now, rearranging variables, we can see that dv by dt dx can be written as dv dx by dt. Also, at displacement x1, we know v equals 0, and at displacement x2, we know v equals velocity. So we can now rewrite our equation as the integral from 0 to v of m over 1 minus v squared over c squared to the power 3 over 2 dv dx by dt equals kinetic energy. This allows us to integrate using velocity. So we have the given expression. As dx by dt equals velocity, this can now be written as the integral from 0 to v of mv over 1 minus v squared over c squared to the power 3 over 2 with respect to velocity equals kinetic energy. The next step is to perform the integration. Consider integrating mv over 1 minus v squared over c squared to the power 3 over 2 with respect to velocity. The limits are removed to simplify matters. We use the substitution u equals 1 minus v squared over c squared. This means that du by dv equals minus 2v over c squared, and dv equals minus c squared over 2v with respect to u. So mv becomes mv times minus c squared over 2v equals minus mc squared over 2. And we notice this is the first appearance of mc squared. As such, we now have the integral of mv over 1 minus v squared over c squared to the power 3 over 2 with respect to velocity equals minus mc squared over 2 multiplied by the integral of 1 over u to the power 3 over 2 with respect to u. We use the integral u to the power n du equals u to the power n plus 1 divided by n plus 1 with n equals minus 3 over 2 to see that the integral of 1 divided by u to the power 3 over 2 with respect to u equals minus 2 over the square root of u. This gives the integral of mv over 1 minus v squared over c squared to the power 3 over 2 with respect to velocity equals minus mc squared over 2 times minus 2 over the square root of u. Replacing the substitution for u equals 1 minus v squared over c squared, we get the integral of mv over 1 minus v squared over c squared to the power 3 over 2 with respect to velocity equals minus mc squared over 2 times minus 2 over the square root of 1 minus v squared over c squared. Simplifying, we have the integral of mv over 1 minus v squared over c squared to the power 3 over 2 with respect to velocity equals mc squared over the square root of 1 minus v squared over c squared plus a constant of integration. Reintroducing the limits, we can see that kinetic energy equals the integral from 0 to v of mv over 1 minus v squared over c squared to the power 3 over 2 with respect to velocity. So, evaluating the limits, we are finally left with mc squared over the square root of 1 minus v squared over c squared minus mc squared. Put simply, kinetic energy equals mc squared over the square root of 1 minus v squared over c squared minus mc squared. So we can say that mc squared over the square root of 1 minus v squared over c squared is equal to mc squared plus kinetic energy, or the total energy E of the mass is E equals mc squared over the square root of 1 minus v squared over c squared, which is equal to mc squared plus kinetic energy. So, looking closely, we have seen that E equals mc squared over the square root of 1 minus v squared over c squared, which equals mc squared times 1 over the square root of 1 minus v squared over c squared, or E equals mc squared over the square root of 1 minus v squared over c squared, which is equal to mc squared times gamma, or mc squared times gamma equals mc squared times 1 minus v squared over c squared to the power of minus a half. However, the velocity v is inevitably going to be much lower than the speed of light. As such, using the binomial theorem, we can expand 1 minus v squared over c squared to the minus a half to give mc squared multiplied by 1 plus v squared over 2c squared plus v is much lower than c, making the remaining terms somewhat irrelevant. So, we now have E equals mc squared multiplied by 1 minus v squared over c squared to the power of minus a half, which is equal to mc squared multiplied by 1 plus v squared over 2c squared, which is equal to mc squared plus mc squared v squared over 2c squared, or the total energy E equals mc squared plus mv squared over 2. We can see that mv squared over 2 represents kinetic energy when the mass is moving. When the mass is at rest, V equals 0, and this expression for kinetic energy disappears. Therefore, we can see that E equals mc squared, and this energy represents the energy of the mass when it is at rest.